Next, 3. Again, definitely this is hypothetical case. We speak about it as spherical capacitor also later. I spoke about it yesterday also. Suppose I have a hollow spherical conductor of radius A, charged with plus q coulombs. Another concentric hollow spherical conductor of radius B, charged with minus q coulombs. Minus q. Because of which q number of flux lines will get emitted from the positively charged inner surface, outer surface of the inner sphere, and get terminated on the negative charge. Total charge in this system is 0. Because of the mutual attraction, positive charge will stay on the outer surface of the inner sphere, and negative charge will stay on the inner surface of the outer sphere, because of which field inside the inner sphere is 0 because there are no flux lines, and field outside also 0 because whatever may be the spherical surface that you talk about here, the total amount of charge enclosed by that spherical surface of radius r greater than B. Total charge is 0 because these two charges are together containing 0 charge. So the only place where we will be able to see the field is what? In between, for r between A and B. I spoke about it, right? Which is q by 4 pi epsilon r squared for A less than or equal to R less than or equal to B. And 0 for R less than A and R greater than B. What is the graph of it? If I want to draw as a function of the distance from the center, till A it is 0, after B it is 0. But it has discontinuity because at any surface charge, I told you, right? It is by A lesser, decreases to this value is q by 4 pi epsilon A squared. In between it is q by 4 pi epsilon R squared. Ultimately at B it is q by 4 pi epsilon B squared. Correct? This is how the field strength varies. You know that at every surface charge, there should be a sudden change in the flux density, and hence the field intensity in the perpendicular direction. What is the amount of change? Change is equal to magnitude of the surface charge. Q by 4 pi epsilon A squared is the surface charge on the inner sphere because Q charge is distributed on the flux density is Q by 4 pi A squared. Q charge is distributed on the sphere of radius A. Charge density is Q by 4 pi A squared. That is the amount of discontinuity, 0 to that value. Ultimately, at the outer sphere, Q by 4 pi B squared is the surface charge density. From that value, suddenly, if I go out, there's a discontinuity. It becomes equal to 0. Let's come to this now. Hollow cylindrical surface of radius R having infinite length. Like this, it is going to plus infinity and minus infinity. I want you to follow this properly. It is a hollow cylinder of radius A with this as its axis, and it is extending. It is of length infinity. Concentrate. Because it is a surface, let rho s be the charge density on the surface. Hey, the circular top and bottom surfaces are not there. They basically go to infinity. It's not a box-like cylinder. It is just an open cylinder, right? It's a pipe. Thin pipe. If rho s is the charge density, look at it now. The top view of this will be a circle of radius A. Charge will be basically like this, because of which on any plane perpendicular to the axis of the cylinder, field lines are like this. Correct? They are actually radial lines in the cylindrical coordinate system, the front view of which will appear to be like this, right? I think this is the second time we are drawing such surface. They'll be going out, but right, radially like this. The field is not spherically symmetric, but it is cylindrically symmetric, where it is only radial component that will be there here. Because charge resides on the outer surface, inside the cylinder, field is 0. Outside the cylinder, it is of infinite length now. If I want to determine the field at a point which is at a distance r from the axis of the cylinder, I need to consider one more coaxial cylinder of radius r passing through the point of interest and length L. L can be infinity also. There is no limit. I spoke about it. From top, the top view of it will look like this, correct? It is a coaxial cylinder of radius r greater than or equal to A. What is the flux density? Flux density d bar is equal to 0 for r less than A, distance from the axis in the cylindrical coordinate system. For r greater than or equal to A, please tell me what is the amount of flux passing through the cylinder of length L? At least think about it and keep it with you, the answer. Then I will tell. Rho s is the surface charge density present on the surface of this hollow cylinder of radius A. In fact, even if it is a solid cylinder, when it is charged, it comes onto the surface only, truly speaking. It is present on the surface of the cylinder. Rho s is the surface charge density within the cylindrical surface of radius r and length L. Whatever is there on the inner cylinder of length L and radius A. Surface area is 2 rho s times 2 pi a L. Correct? Per unit length, it is rho s into 2 pi a. Per length L, it is, this can be considered to be rho L. Correct? By the curved surface area of the cylinder of radius r is 2 pi r L. Rho L by 2 pi r only, you have to see this. You can assume that it is the line charge of line charge density rho s into 2 pi a on the axis of the cylinder. Earlier in the spherical surface charge case, I told you that spherical charge or volume charge. I told you that you can assume that all the charge is concentrated at the center as a point charge and calculate the field outside the charge distribution. In the same way, the flux density here rho s into 2 pi a, do you agree that it is rho L? Charge per unit length of the inner cylinder? Yes, L is equal to 1. It is uniformly distributed, because of which I need not take delta S by delta A, any area into Q. That's a Q by any area. That is actually rho S into 2 pi A is rho L by 2 pi R. R is the distance from the axis. If this were to be rho L, this were to be the line charge, right? There were to be a line charge inside with rho L equal to rho S into 2 pi A. The field is same at that point, whether it is line charge of this rho L or cylindrical surface charge of radius A and surface charge density rho S, divided by 2 pi R L. So what is E bar? For R greater than or equal to A, because of which E bar at any point is 0 for R less than A.
Rho L by 2 pi R.
Rho S into 2 pi I will put. 2 by 2 pi get cancelled out now, because rho S is given now. Rho S into A by epsilon times R for R greater than or equal to A. You have to see this. Rho S is there on the outer surface. If R is equal to A, what is the electric field intensity? Rho S by epsilon. Because surface, I told you, right? If it is a plane surface, if it is rho S by 2 above, rho S by 2 below, rho S by 2 epsilon we saw on the surface. It's normal. Here also it is normal to the surface, because of which at R is equal to A, it is rho S by epsilon. Because other side charge is not there. Entire rho S is there on the outer surface only, because of which it becomes rho S by epsilon at R is equal to A. R less than A, it is 0. Because rho S is given. If it were to be rho L given, rho L by 2 pi epsilon R. If it is rho S is given, rho S into A by epsilon R. Next case. This is the first case cannot be finite length cylinder. Why? If it were to be finite length cylinder, charge would have accumulated on the circles below and above. That's all. It will not be there on the surface. That's why I took it as infinite length. But the most important case for us, for the sake of talking about electric field intensity, to calculate about the potential difference, to talk about the capacitance of a cylindrical capacitor. When it is cylindrical capacitor, capacitance per unit length of the coaxial cable, resistance per unit length of the coaxial cable, conductance per unit length of the coaxial cable, everything is determined because of this. We are going to see. To determine the resistance per unit length of the coaxial cable, conductance per unit length of the coaxial cable, as well as the capacitance per unit length of coaxial cable, the case that we are discussing becomes extremely important. So concentrate, because for everything electric field intensity is required for me at any point in between. Yeah, whether it is a capacitor or the coaxial cable, it is of finite length. Coaxial cable, there will be inner conductor. I'm considering hollow A. Another coaxial cylinder of radius B, of let us say length L. There is axis coaxial cylinders B. Again, one of the inner conductor is positively charged. Normal it is. Core of the coaxial cable. And the outer sheath of the coaxial cable is minus charge, negatively charged. Definitely, positive charge on the inner cylinder is same as the negative charge on the outer cylinder, plus Q minus Q. Please think about the electric field intensity, where it will be there. Definitely, R less than A or greater than B, there will be no electric field. Very simple case, but very extremely important case for us. Now, if Q is the charge on the inner sphere, Q is the charge on the outer sphere, totally Q number of flux lines will go from the outer surface of the inner cylinder to inner surface of the outer cylinder. Only the curved surface comes into picture because they are hollow. Flux density D bar 0 for R less than A, 0 for R greater than B. Why? Because if you consider outside a point and the cylinder, the total charge enclosed in the cylinder is 0. Anyway, Q flux lines will start and then get terminated on the negative charge, because of which inside the inner cylinder and outside the outer cylinder there will be no field. Inside, in between, what is it? To determine the field intensity at any R in between A and B, you need to consider an intermediate cylinder of radius R passing through the point of interest, which is coaxial to the given cylinders, because of which Q by it is 2 pi R L. You agree this? Q is the total charge. L is the length of the cylinder. 2 pi R into L is the total area through which Q coulombs of flux is passing through. For A less than or equal to R less than or equal to B. Because of which the electric field intensity E bar is also equal to 0 for R less than A, Q by 2 pi epsilon RL radial, right? Here in cylindrical aero for R, A less than or equal to R less than or equal to B, 0 again for R greater than B. Radial component in cylindrical coordinate system. It is. Check it once. Q by 2 pi epsilon RL. This is important for us to talk about that cylindrical electrolytic capacitance of cylindrical electrolytic capacitors, capacitance of coaxial cable per unit length, resistance, conductance. Okay, check it once. At least series conductance, sorry, shunt conductance and shunt capacitance. We need this. If I again sketch it. How will it be? As a function of the distance from the axis till A, it is 0. Hey, what is the value of it at A? Q by 2 pi epsilon AL, which is the surface charge density. Correct? Q by 4 pi epsilon AL. Later on, it decreases as R increases beyond A. Then we'll reach Q by 4 pi epsilon BL at B, beyond which it is suddenly 0 because there is a surface charge density of Q by 2 pi now, not 4 pi. Sorry. 2 pi. 2 pi epsilon. This is how it varies. Looks to be the distribution as a function of the distance from axis is like this. Like no concentric spheres. Distribution as a function of distance from the center of the concentric cylinders. Concentric spheres. Coaxial cylinders here. In the same way. Hypothetical application. Where it is a cylindrical volume charge of infinite length and radius A. Rho V is the volume charge density. Please think about it. It is of infinite length. I don't want to talk about finite length because if it is finite length, from top and bottom also field lines will come out. Only if it is of infinite length, the field will be of cylindrical symmetry. I want to determine the field at any point outside and inside also now. Like the solid sphere in which charge is distributed over the entire volume with charge density rho V, considering it to be uniform. Volume charge density is uniform. There are so many cases. If you want, if electrostatics were to be there in gate, the discussion would have been for about 6 to 7 hours. Only on the applications of Gauss Law. There are so many good things are there actually. But because it is not there, we are not much worried now. I'm trying to give an entire concept required for us to understand this subject for the sake of different subjects. Now, check. The field is again cylindrically symmetric, no doubt about it. Because this can be considered to be composed of so many cylinders of different radii. Every thick cylinder, solid cylinder, is composed of infinitely many thin cylindrical surfaces with their radius going from 0 to infinity. Each creates the field of cylindrical symmetry, because of which overall this thing also will create this field of cylindrical symmetry. Now let us consider, because it is symmetric, I want to determine the field at a distance r inside. Or inside. What does it have to do? Field at a distance r inside. I have to draw a cylindrical surface of coaxial radius r of length L. Correct? Let us say of length L. We consider this because at any point on the cylinder, field is same. Field is same because flux density is same. What is the flux density? For d bar. For r less than or equal to A. What is it? Please respond if you can.
Rho v pi r square L by 2 pi r L.
Rho v by
2 pi r L.
rho v total charge. We want to know first of all the total charge inside.
Total charge is rho v by pi r square L.
Hey,
The volume
Rho v
density
into pi a square.
Yeah,
rho v into pi r squared L. Volume of the cylinder of radius r is what?
Pi a square.
Pi r squared L. Correct only. Pi r squared is a circular disk length L. Correct only.
Yes, sir.
Rho v into pi r squared L is the total charge inside the cylindrical surface of radius r less than a and length L. Flux density divided by 2 pi RL is the surface area, curved surface area of the cylinder of radius r and length L. Am I right? Correct only, no? Next, r greater than or equal to a. I have to draw a cylinder of radius r, coaxial to the original cylinder. What is it now? Rho v into pi a squared L. That's all. Beyond which charge is not there. This is the total charge enclosed by the imaginary closed surface. No, imaginary cylindrical surface of radius r, which is coaxial to the cylinder. Correct? No, pi a squared L. Rho v is the volume charge density. I want to know the total volume charge inside divided by 2 pi RL for r greater than or equal to a. Please check it once. So what is electric field intensity? For the sake of, this is academic interest only. Hypothetical case, E bar is equal to what? By epsilon should come, pi will go. Rho v r by
R
2
by
epsilon.
2 epsilon.
Huh? Rho v r by 2 epsilon for r less than or equal to a. Here also, it is increasing linearly with r. Then rho v a squared by
2 r.
2 epsilon r. Rather, I'll just put it as 2 epsilon r. R greater than or equal to a. When I write less than or equal to, greater than or equal to, at a, both should give me the same answer. Correct? At a, it is rho v by rho v a by 2 epsilon in both cases. R is equal to a. If I look at the variation of the field as a function of the distance from the center, here also it increases linearly until the surface and reaches rho v a by 2 epsilon. Rho v a by 2 epsilon. Aero everywhere in cylindrical coordinate system. Then 1 by r is nonlinear decrease beyond this at a. That is the value. Beyond that, at any distance r, it is rho v a squared by 2 epsilon r, right? Given by this line. This is how the field varies as a function. In any direction you go from the axis out, this is how it increases linearly first till the surface and then decreases non-linearly.